All right, everybody. Welcome to Martlets Talk Season 4, Episode 1. I'm today's moderator. My name is Binbin Ying. I'm currently a postdoc at MIT, working on ingestible electronics and ingestible robotics with Professor Giovanni Traverso and Professor Bob Langer. Now, let me introduce today's agenda. So in the opening part, I will have a brief introduction of our society, as there are many new friends attending today. Then Professor Dong will help introduce today's speaker. Professor Dong currently is an assistant professor at Vanderbilt University, and he did both his postdoc and PhD training with Professor Martin City from CMU and Max Planck Institute. Then Professor Truby will share his research with us. His talk will last around 40 minutes. During his talk, we hope the audience can mute yourself. And after that, we will have a 30 minutes QA session. Professor Dong will lead the QA session with me. And Jen, can you show the QA rule? Okay, never mind. We will talk this later. So you are encouraged to type your question in the QA box or raise your hand during the QA session, and we will promote you to our panelists. So, okay, now let me have a brief introduction of our society. So our society, the Martlets Society, or TMS for short, is a non-profit organization that aims to build a community for young scholars to freely and equally building connections, share this work, and exchange thoughts. In the last 3 seasons, we have already organized 4 types of events: Martlets Talk for academia, the WBA Talk for non-academia, and the TMS workshop for skill set building. And also we have like a special issue from the senior and seasoned professor. And if you want to know more about us, please visit our website and subscribe our WeChat, LinkedIn, and Twitter channels by scanning the QR code below your in the slides. Now I will give the floor to Professor Dong. Professor Dong.
Yeah, all right, thanks Binbin for the introduction. So now I'm going to introduce Professor Truby about his talk today. So Dr. Truby actually got his PhD from Harvard and a postdoc from MIT. He's currently an assistant professor in the Department of Material Science and Mechanical Engineering at Northwestern University. So now he's leading the robotic matter lab. His lab is mostly specializes in functional soft materials, additive and digital manufacturing, design, control of soft robots, and many other things related with soft material. So he has multiple awards, including an outstanding paper award from 2019 RobotSoft, and he also got a very prestigious 2022 Air Force Young Investigator Research Program Award. So today he's going to talk about his vision and research in designing the robotic materials from sensorized soft and architecture matter. So let's welcome Professor Truby for his talk. Yeah, Ryan, it's yours.
Let me switch over and get this up. Can everybody see this okay? Perfect. All right. Well, happy Saturday, everyone. It's great to be with all of you. I really want to begin by just saying thank you to Professor Dong for the kind introduction. And most importantly, I want to say thank you to the Martlets Society for not only the very kind, but very patient invitation to be here today. It's been a really awesome time at Northwestern building out a new research group, but with that comes the unique stresses and limited sleep of building such a research program. I really have 2 key objectives today. The first is to share with all of you kind of the vision that we are working forward to in my group here at Northwestern. It's a little premature to talk about the exact things and some of the preliminary data that we're getting, but we are working towards this vision of designing soft robots, or bio-inspired robots for that matter, as robotic material systems. And so I'll talk a little bit about what exactly we mean by that and where we're going forward in this vision. And to give you kind of some insights and some kind of vignettes, if you will, of ways in which we've explored these ideas. I will talk about ways in which we've been thinking about designing and fabricating soft sensorized robots, as well as new types of electrically driven soft robots based on architected materials like the type of system that you see here in the video. There we go. All right. So my research is very much inspired by this stark performance gap that we have so long observed between built machines and biological ones. Robots like those that you see on the left are inevitably going to shape the future of modern society. They are already impacting the way we think about transportation, automation, manufacturing, infrastructural development, and much more. But these types of robots are really only going to have their impact for the foreseeable future in environments that we can carefully regulate, control, or contrive. In direct contrast, living organisms have this remarkable ability of robustly and reliably thriving in real-world environments, environments that are characterized by their harshness, their complexity, their unstructured nature, and their dynamicism. And so if we could figure out ways of closing this performance gap, we think that we would tap into some pretty unprecedented opportunities for solving key societal and global challenges by having autonomous agents be deployable in the real world. Now, historically, there have been a number of approaches robotics has taken to try to bridge this performance gap. We've seen really interesting and exciting opportunities in bio-inspired robotic systems and swarm robots, even thinking about going at unprecedentedly new length scales and even biohybrid designs. But we are particularly interested in this space of soft robotics, something that's kind of originally got its origins as material robotics, which places the emphasis on closing this gap, not through computational advances, but rather material ones. And so I really kind of want to drive home that our overarching research objective is rooted in material science and engineering. And we do think that closing that performance gap is going to require not just computational advances, but truly materials-driven ones. Soft robotics in many ways is bringing soft materials into the robotics design mix to appeal to a side of machine intelligence that historically has been ignored by robotics engineers. Most of robotics has been kind of predicated on the fact that we need to think about advancing intelligence computationally, thinking about algorithmic development, thinking about control strategies, because robots have historically been systems based on motorized mechanisms. But nature does teach us that there is something physical to intelligence. There is a role for the body, not just the brain, to play in our general sense of autonomy and intelligence. I really, truly want to emphasize that these are not new ideas. These have been explored by phenomenal leaders. Many people on the panel know and have worked with Professor Metzidi, who has done phenomenal work in trying to help us understand the importance of both sides of machine intelligence. But I do just want to iterate that I think that this is what soft robotics aims to do. I also want to drive home a point today that I don't think we do this very well at all. In fact, I want to make the argument today that we are so laser focused on just focusing on the physical appeals to intelligence in how we create new types of soft actuators or use these systems. So if you think about soft robotics, we are kind of focused on using fluidics or dielectric elastomer actuators to enable these types of physically intelligent machines. But the requirements for actually actuating these systems are not very compatible with the controllers and the power supplies and the sensors that are ultimately required to still give this robot a kind of a brain. In effect, I think in soft robotics, many of our challenges stem from the fact that we have so focused on trying to create better soft robot bodies that we forgot to give those bodies brains. The types of controllers, the sensors, the practical power approaches that are actually needed to create these machines. You can literally see this disconnect, this lack of bridge between the physical and computational in soft robot design. This is wonderful work. I love this robot from Mike Tolley at the University of California, San Diego, where they clearly show us these beautiful bio-inspired actuation modes, but these actuators can't bear the payload of the hardware needed to actually power them. We manufacture these systems in such a way that it kind of complicates how we might sensorize the bodies. We don't have sensors. We don't have good control strategies. We have tethers. I think many of these kind of things very much highlight the fact that we're not doing a good job of creating physically and computationally intelligent soft machines. And so to that end, our group is focused on this idea of how do we not just design soft materials for new actuators? How do we not just design soft materials for soft sensors? how do we actually think about bringing together actuation, power, perception, and control capabilities into single material systems? Because at the end of the day, all of these functionalities are kind of inextricably linked. And if I'm not thinking about all of these at the forefront of soft robotic design, I'm going to run into this trap of not creating a machine that appeals to both of these equally important sides of machine intelligence. And so we imagine creating material systems that specifically work to enable these integrated multifunctionalities. And importantly, this is going to require us to take a new lens to science and engineering of robotic materials. We are going to have to focus on new ways of processing for these integrated functionalities, because those integrated functionalities are critical for really helping us explore not only this closing of the performance gap, but practical applications for soft machines. And so if you're interested in kind of reading a little bit more as to how we've been thinking about this, I want to kind of shamelessly plug a little perspective piece that we published last fall at Accounts of Materials Research. And the editorial board was kind enough to feature us on their front cover for that issue. So in many respects, we have been thinking about robotic materials. And I want to make the case that this little system that I made called the Octobot is, in a sense, our very first robotic material. So this machine that you see called the Octobot is something that I designed in very close collaboration with my colleague, Mike Vayner, who's now a professor at the University of Wisconsin-Madison, when we were in Professor Robert Wood and Jennifer Lewis's groups at Harvard University. And the general idea of this system was to think about replacing hardware by turning to a chemical fuel instead of rigid power supplies, turning to microfluidic logic-based controllers as opposed to rigid computers. And in this sense, what we were able to achieve was the selective decomposition of this liquid hydrogen peroxide fuel within 3D printed catalysts that would produce a gas that we could use for actuation. And so in many ways, this is an underwhelming machine, but by architecting the geometry of kind of plumbing within this elastomeric composite, we are able to showcase a composite that integrates actuation, power, and control simplistically within a single composite. Many groups are now working on thinking about fluidic sensing in these types of systems. And I kind of want to just hint today at where we are actually going forward, inspired by the Octobot as kind of a first artifact of a robotic material. Specifically in my group, we think that the best way of thinking about bringing together all of these important robotic capabilities is through returning to electronically integrated approaches to how we think about actuation, to how we think about control, to how we think about sensing, and also power as well. And so kind of motivate why we think electronic integration is the way of kind of the future in this space, as opposed to something like pure fluidic integration approaches. I want to talk a little today about how we have thought about sensorizing soft robots, specifically creating new types of sensorized soft actuators. Control in soft robotics is incredibly hard, not only because of the challenges of sensorizing soft robot bodies, but at the end of the day, what do you actually do in a feedback context? How do I actually control a very difficult to control system? And so I'll talk a little bit about how we hope to bridge that gap with machine learning. And then finally, I do want to kind of tease something that is of kind of huge interest to our group right now at Northwestern. And that is thinking about returning to electric actuation, not through high electric fields or not through thermomechanical response, but literally creating new types of architected materials that would allow us to return to the use of conventional, robust, easy to access servo motors. So I first just kind of want to dive into this sensorization side. Again, in this idea of appealing to physical intelligence, in this idea of kind of working towards pneumatic actuators or dielectric elastomer actuators, we've created materials and manufacturing methods that make it difficult to easily sensorize these robots. And so most soft robots that you see actually don't have any sort of integrated sensors. We don't have good closed loop control strategies for these robots. When we started this work, some of the kind of prevailing strategies was to figure out ways of carefully molding off-the-shelf flexible bin sensors like those that you see here within the neutral axis of these pneumatically actuated fingers. So this is work from MIT. This is work from a former colleague of mine, Robert Katchman, and my postdoc advisor, Daniela Roos, where they were able to hold objects and in a kind of preliminary way predict or recognize what object was in the soft hand's grasp. I'll talk later in the talk a little bit about some other sensing approaches, but I do just want to give a highlight to Professor Robert Shepard's group and the incredible work they're doing with elastomeric waveguides as sensors. Basically, the idea here is to sensorize soft actuators by putting in stretchable waveguides that allow us to translate optical power losses during their deformation into modes of sensory feedback. Now, the big kind of takeaway that I want to emphasize here is that in some instances, these types of sensors aren't exactly soft. So those bend sensors can bend, but they're not stretchable. It's difficult to think about designing easily these systems when you have to manually assemble or manually mold and then kind of place them into these actuators. So it's limited design flexibility, limited softness, ultimately limited functionality, and therefore difficulty in kind of streamlining the fabrication of these devices. We made the Octobot with a technique called embedded three-dimensional printing that I'll be talking a little bit more about in a few slides. But as we were working on Octobot and recognizing the opportunity of freely patterning different types of functional materials within the bodies of some agent, we wanted to work towards a system that wouldn't be limited in terms of how we might explore bringing specialized functional receptors through sensing networks into these soft robots. Specifically, we wanted to come up with ways of sensorizing soft robots in a manner that would allow us to explore how would that agent have proprioception? How would it have specialized forms of touch? How would it might even have pain or temperature sensing capabilities? And we didn't want to be limited to the type of somatosensory capabilities that we could explore. So we set out to create these systems that we'd call SSAs, or soft somatosensitive actuators. And so SSAs are pneumatically actuated. This is what they look like in a non-inflated state. And if I increase the pressure, I'm going to induce bending, just like any other kind of net or pneumatic actuator. But with these embedded printing methods, I wanted to do a couple things from a sensing point of view. I wanted to figure out, was it possible for us to actually sense curvature? So if this thing is bending, I need to know something about how much it's bending. I also want to know something about, is this intentionally inflating? So I can inflate the sensor, or excuse me, inflate the actuator to get bending, but I can also manually bend this to get bending. And so it would be important to sense if that was intentional. Of course, we want these objects interacting with the real world. And so being able to sense contact was something very important for us as well. And so we set out to introduce within this printed soft somatosensitive actuator, at minimum 3 different types of sensors that we would call curvature, inflation, and contact sensors. I'll talk again more about embedded printing, and I have a short little video clip to show. But the premise of embedded printing is I have some mold, and I fill within that mold an uncross-linked silicone rheologically tailored fluid called a matrix material that would allow me to come in and freely print different traces of different inks that are going to give me functional parts. And so for this work, we are actually working with the mold assembly. We take one layer, pour a matrix material in. After printing whatever's in that layer, we can add a new matrix material and mold layer, pour that in and print, and continue this process. And for this work, we use 2 functional inks. We use a fugitive ink. These are kind of ubiquitous in Professor Jennifer Lewis's group. These are all aqueous gels based on a class of polymers called pluronics. We use this to template out our actuation networks. But really what we needed to do was figure out how to 3D print the sensing ink, which is the red ink that you see here. So I don't have time to go into all the trade-offs of thinking about how to make a better soft sensor. Soft sensors are difficult to create, and we wanted to try to address this question and turn to thinking about printing sensors based on ionic liquids, so naturally ionically conductive fluids. We started working with this organic ionic liquid. It's a molten salt at room temperature called 1-ethyl-3-methylmidazoleum ethyl sulfate. And anytime we're 3D printing, we need to rheologically tailor that ink to facilitate the printing process. We need shear thinning, viscoelastic behavior. And we found that the easy way to do this was to take fumed silica, a very cheap rheological modifier, add it to our ionic liquid, and get these really nice shear thinning fluids. And fortunately for us, this had been done before. People had been looking at solid and gel electrolytes, what happens when I take a nanoparticle and put it into an ionic liquid, and all of a sudden get these nice gels. Now, this was probably the easiest ink I had to make during my PhD. It literally is taking fumed silica and adding it to an ionic liquid and getting this high performance, soft, ionically conductive sensor. On the bottom here, you see our typical kind of rheological curves. We have apparent viscosity versus shear rate, storage modulus versus shear stress, for neat ionic liquids through to 7 weight% of this fumed silica added. And so I'll draw your attention here to the neat ionic liquid line. So again, this is just a fluid at kind of room temperature in no filled state. But as soon as I start adding that fumed silica, I get this very pronounced shear thinning response. I get increasing viscosity. And as you can see, even going from 3 to 7 weight% fumed silica, I can span almost 2 orders of magnitude in storage modulus and about 2 orders of magnitude in yield stress. So basically a very easy knob to kind of sweep through a whole different array of rheological behaviors to facilitate embedded printing. So this quick video will show you a little bit about the process. The entire process takes about 90 minutes, but this is us printing the pluronic ink within that actuator matrix. We'll then put that third layer on, our third matrix material, and this is that sensor ink being printed. Again, all of this is uncross-linked. We print in a free-form way. Once printing is done, then we throw this in the oven, and we're left with structures that look like this. The fugitive ink can be removed by just refrigerating the actuator and pulling that ink out by vacuum. But in short, what we have here is in 90 minutes, an opportunity to create a 5-material construct. That'd be very difficult to do with kind of any existing method. And we achieve this by using the mold to kind of globally program form, and then we print 2 different inks to give all the different functional features that we need. And so in this particular picture you see on the top here, this is the curvature sensor running along the top or the dorsal side of that actuator. The blue features are, again, that pluronic ink. These are going to be my actuation network. And so you can see kind of the inflation sensor weaving right around that set of actuation bladders. And then if I actually turned the tip over and showed you the underside, you'd see this contact sensor meander. And that's where we're going to make contact with objects. And then we can tune the mechanical properties of each matrix material. We can terminate all the kind of leads and inlets for our sensors and actuation network within this tougher actuator matrix that you see here. So I kind of want to quickly just walk through how these sensors actually perform. And to do that, I'll kind of give you this simplified view of these actuators. So all the inflation, curvature, and contact sensors are resistive sensors. So the inflation sensor is shown here in green in the actuated state and on the bottom in the unactuated. That inflation sensor is weaving around those inflation bladders or the actuator bladders. So as I inflate or increase internal pressure, I'm going to compress my inflation sensor and get a resistance increase. The curvature sensor lies on top of the device. So as I inflate, I'm going to bend and get a resistance increase. Similarly, on the bottom side where I have my contact sensor, if I apply contact pressure, I'm going to collapse cross-sectional area and get a resistance increase. And fortunately, that's exactly what we saw. These were designs that we intended and were able to see in our characterization of free and block displacement of these actuators. So on plot A here, what we're doing is we're taking that actuator and just allowing it to inflate without actually hitting an object. And you can see a nice resistance change with inflation pressure from our blue curvature sensor. We get a kind of nonlinear response from the inflation sensor. And then appreciably, there's no real big resistance change from that contact sensor. Now, if I change the study by having some rigid obstruction and freely inflate against it, I'm going to constrain bending. And so I don't get as a pronounced response from my blue curvature sensor now. The green inflation sensor is pretty much the same, and that orange contact sensor begins to show me some clear resistance changes. Now, in these block displacement studies, we're not guaranteeing pure intimate contact rather with that meander as I show here in this illustration. But you can definitely see if I directly push on that meander that I get very large resistance changes from that contact sensor. Maybe another way of showing this kind of more clearly is to see what happens when we actuate, deflate in these free and blocked contexts, where each time we actuate to a new pressure, that pressure is increasing. So in the top row here, you see the context of free displacement. Again, we see a nice response from the curvature sensor and appreciably no response from that orange contact sensor. But then when I block that system, I get a very clear response now from the contact sensor and reduced response from my curvature because it's not able to bend as much. Now, importantly, we get really interesting insights when we're not intentionally inflating. And so in this case, I'm manually kind of manipulating the finger here. And you can see from the green inflation response that I don't really see a resistance change there. This is still a very soft material, so no matter how I'm deforming, at some point I'm going to deform it to some extent, but not as much as if I was inflating and compressing that green sensor. But importantly, what you can see here are a couple of really exciting trends. One is that the curvature and contact sensors lie on either side of a potential neutral axis based on the direction of bending. So when I unintentionally bend upward, I get my resistance change sign to swap for the curvature and contact sensor. Whereas if I bend downward, those kind of sign changes are restored again. Really interestingly was when we were like flick and kind of perturb the system. You could literally sense that damped harmonic response as it would go back to its steady state. And in this paper in the SI, we have these like beautiful curves showing the high resolution of that sensing. And that's something you simply wouldn't achieve with other types of soft sensors that are hysteretic or time varying. And really what I want to emphasize here is that each time we go back to some initial state, we are returning to our initial resistance, which is indicating that we're not having these types of hysteretic responses or time varying nature, because we're simply working with a rheologically tailored ionic liquid. So this video here just shows you a little bit about how these curvature, inflation, and contact sensors can give rise to kind of bio-inspired ways of proprioceptive, kinesthetic, and tactile sensing. And this is just me kind of interacting with the gripper, holding a ball. And importantly, when I fully deflate this actuator at the end of the study, more or less all of those sensors go back to their original resistance value. And that kind of robust, reliable performance is really critical for thinking about control. So when I moved to MIT, I really wanted to kind of close the control loop on a very simple gripper. I wanted to create algorithms that would allow us to autonomously grab objects with these grippers. One of the really cool things about embedded printing is, of course, if I want to change the general shape, I have to change the mold, but otherwise I just change G-code and the path planning for my actuator and sensor inks. So instead of just one actuation network, I could actually think about having two different actuating networks, which would allow me to selectively actuate either the tip or the base of my finger. And this is something that's kind of hard to do when I take a pure molding approach to creating pneumatic actuators. What was really exciting about this was I could also create kind of regionally specific curvature sensors. So I put one curvature sensor called the short curvature sensor spanning along the base actuator. I could have a long curvature sensor that spanned the entire length of that. And I could similarly create short and long contact sensors. In short, I could create multiple degrees of freedom of actuation, and each of those degrees of freedom had their own curvature and contact sensor. So kind of truly distributed proprioceptive and tactile sensing. This kind of capability became critically important for us as we started working on these algorithms. So I'm going to let these videos play, and hopefully Zoom's going to collaborate with us here. But on the left, what you see is what happens when we try to feel for an object and there's no object there. What you see this gripper doing on a UR5 arm is in a tactile servoing way, trying to feel for an object. And we want it to initiate a grab when it feels it, all based on the sensing that it receives from those printed tactile sensors. What's important to note is how this thing is kind of feeling. So on the top row, you'll see that there's full finger actuation. Whereas on the bottom row, you'll see that I'm trying to feel for an object just by inflating the base, not the tip. And I get a very different grasp in doing so. So let's see what happens when I put an object there. We have an algorithm in place where we want to initiate a grab when two fingers have some contact resistance change cross a threshold. If I'm feeling for this object using full inflation, I actually get this kind of positioned up higher grasp. Whereas I inflate only the base, I get this kind of deadened grasp. And this has some important insights. What's actually happening here is I'm over torquing as I'm trying to feel that object. And I'm triggering this sensor to think that it's actually grabbed the apple. On this other side, I have a weakened grasp. It's kind of deadened. These contact sensors are right here on the underlying base, and they're getting much more kind of reliable contact with that object. I don't do anything. The algorithm naturally positions the hand further down the object so that when the algorithm tries to initiate a grasp, it has autonomously postured its hand further down the object, giving me a more successful lift up. And so without changing anything, I can look at this with a bunch of different objects. And it's kind of weird to see how it immediately senses like the chips, but you'll watch how it struggles on this compliant object trying to like posture its hand all the way down before it tries to initiate something. On the right here, you see some difficulties. We can't pick up very heavy objects because that's a limitation of the actuator. And for our particular system, it's difficult for us to lift kind of high or rather low aspect ratio type features like the banana that you see here. But no matter what, in all these cases, we were able to successfully initiate a grasp. And if it was able to be lifted, we were able to successfully pick it up. So in short, I wanted to kind of show you this because we're looking at new ways of sensorizing soft actuators that are fully 3D printed. We have now created 2 degrees of freedom in actuation with 4 distributed sensors in one 90-minute print session. And we've developed some basic algorithms for thinking about how to autonomously feel for and posture our hand around objects before grasping them. In short, what we have is now a lot of opportunities to think about how to better control these things, how to think about more bio-inspired actuation, and a whole lot more. These types of algorithms are great. They're simple. They allow us to do really cool things. But in the context of more robust control, what we're realizing is that we have to turn more and more to machine learning. And so the reason we're turning to machine learning is that model-based control of soft robots is incredibly difficult. To me, this is one of the coolest soft robots out there. This is work from former colleagues of mine, Robert Katchman and Cosimo della Santina. This is an elephant trunk inspired arm. It's a 3-segment arm where each segment has 4 pneumatic actuators. They developed this very complex model-based approach for dynamically controlling the motion of this arm. But unfortunately, that arm actually has no sensors in it at all. It's using motion capture, which is a kind of exogenous vision-based sensing strategy. As soon as I want to ask this to work in the real world, it's going to say, well, where's my camera showing me how I'm moving? If you want to actually robustly control a robot, we need to figure out right now how to integrate specific tactile and proprioceptive sensors within these bodies so that our control strategies aren't using motion capture. They are working with the distributed sensors that we could provide these bodies. Machine learning has a critical role of helping us understand how to make sense of these sensors. We've seen really awesome work on how machine learning could help us predict something about the deformation mode of soft actuators that are sensorized with liquid metals. Rob Shepard's group, again, doing really interesting work predicting shape change of non-actuating structures with their optical waveguides. And then again, really great work coming out of UCSD and Mike Tolley's lab, where they're taking piezoresistive sensors and recurrent neural networks, specifically LSTMs, to predict tip position and force in bending actuators. In short, we still don't need the ability to predict the full configuration of a soft robot if we want to do that type of dynamic motion control that I showed previously. And while there has been a lot of work in this space, this is still kind of a key missing need and something that we were very much inspired by. So we took this same arm and decided, well, let's figure out a way of easily sensorizing it. It's very difficult, as I hopefully alluded to in the previous part, of sensorizing very complex robots. We had this very complex elephant trunk inspired arm, and we needed a very easy way of sensorizing it. So I'll talk about how we do that with Kirigami and off-the-shelf sensors. These sensors are going to be inputs to neural networks, and using kind of motion capture data as ground truth, we train these neural networks to take sensory inputs from these sensor skins and then convert it to a prediction of configuration. And I'll talk a little bit about this pipeline and the challenges that we face in this space. I showed you on the previous kind of part here this very complex 3D printing method to sensorize soft robots, but an arm like this is really difficult to 3D print. It's difficult to sensorize. And so we reached for off-the-shelf conductive silicones. These are commercially available. And we were able to really fabricate these easily through laser cutting. And we decided, well, let's take on some Kirigami designs. Through cut pattern, I can change the sensitivity, the response, the extensibility of these systems. And we started putting them on the sides of these arm segments. We worked with 4 different patterns that we'd call circle 45, -45, 1D, and 090 patterns. And we could take these 4 different sensors with different responses and lay them over the molded arm segments that we were making. And so importantly here, that model that Cosimo and Robert had developed is very much dependent on the very form and the very mechanical properties of this arm. So we didn't have to change anything mechanically or from a design perspective about that arm we were able to conserve that design and simply kind of plasma bond these kirigami surfaces to that surface. So this is the fully sensorized arm. Again, it's 3 segments. We call it segments 1, 2, and 3, with the segment 3 being on the bottom. You can see that kirigami sensor skin on the outside. And many of these types of robots, and the way that Cosimo and Robert had been modeling these, were through piecewise constant curvature models, which are typical for different types of continuous robots. And so effectively, a PCC description for this robot allows me to define for each segment some curvature and some pair of angles describing that orientation in space. And so if I can understand what inputs are going to my system, and I could use the PCC description to kinematically describe my robot in configuration space, then I can understand something about what this robot is doing, say in task space. I can understand something about its position or orientation. And so Cosimo had developed this really wonderful framework for helping us think about where sensors would be useful and helping us predict these different configuration parameters for this type of an arm. What Cosimo and Robert had normally done was try and work with these 2 angles, so describing the orientation of these segments and some curvature delta L. And we would have to predict these for each segment. So Q sub I would be for each ith segment. And what we really want to do with the neural network is figure out how to take the sensor inputs V sub I, of which there are 4 per segment, and back out with a neural network what our kinematic parameters are. As we started working on this project, though, there's a big problem that we were faced with, is that these particular kinematic parameters are not good for learning. I run into singularities, as is common with PCC descriptions, for how I think about theta and phi. If I don't have any curvature, well, then I can describe any phi that I want and still have that description in place. And so we really had to think about ways of extending the PCC description to a learnable subset of kinematic descriptions. And so I'll kind of gloss over this a little bit, but in short, we can take these same geometric considerations and back out 4 unique curvatures describing kind of each side, if you will, of the segments. And so we call these L sub 1 through L sub 4 for each ith segment. We can kind of just algebraically describe 2 condensed terms, delta x and delta y. And now these are kind of what we're substituting in our prediction. And these allow us to avoid those singularities and actually have parameters that are learnable. What you see here is that 3rd segment actuating. We see our sensor responses for each mode of bending each actuator and our corresponding kinematic responses. And so this is very noisy. It's very difficult to kind of comb through and understand, but the big takeaway I want you to recognize here is that these sensors are non-monotonic. They're not very good. We're stuck with the same challenges of soft sensors. We can't use those ionogel sensors we had made previously. We're having to work with these kind of typical time-varying hysteretic sensors, and you can kind of see just it's difficult to do anything from a model-based perspective with these non-monotonic responses. This gives you a kind of sense of what these experiments would look like. We're looking at all sensors here as we're having a full arm undergo what we call these inflation steps. And what we did is we would run these experiments in motion capture, creating huge data sets of sensor responses versus motion capture. And we had to run these arms through a variety of different actuation motifs just to try to capture as much of this time-varying response as we could. And to kind of bring this to kind of a very short message, we were only able to collect about 80 minutes of training data and 13 minutes of validation data before this entire arm would fail, and we'd have to repeat the whole training again. It's pretty common practice to take your validation set and use that as a test set in these kind of projects. And so unfortunately, we did have to do that, but we were still able to make some kind of important insights into this type of work. And so very quickly here, what you can see in the video is that prediction alongside the ground truth. The prediction is the black line that you see here. That red line is black is prediction, the red is the ground truth. And what you can see from this response effectively is that the neural network is helping us kind of predict steady state really well, but we are seemingly filtering out some of the more dynamic responses of the device. These are some predictions from just kind of random actuation. So we apply random pressures at all 12 actuators and we hold that for 3 seconds. And again, you can see here in the video where we're showing prediction and ground truth that we are kind of filtering out that dynamic response. And so it is kind of interesting to us, where is the contribution for not being able to fully predict configuration dynamically? Does that lie something with the materials that we're using, or does that lie something with the neural network design? In short, we had to put a lot of work just to use machine learning to help us perceive for such an arm. And really kind of our longstanding goal is to figure out, how do we take this type of arm and how do we now dynamically control using those sensors as feedback, not just the motion capture. So in the interest of time, I'm going to kind of move on very quickly onto this last part. And this is work that came out last year. We're really excited about it. And it's kind of looking at a very different approach of soft robotic actuation. One of the themes I hope that has shined through is that actuation is tough, and actuation, especially pneumatically, has a number of challenges, in large part that we need bulky, rigid hardware to actually actuate these pneumatic systems. There are a number of ways people are trying to move beyond pneumatics, and specifically in an electrically driven context. One way we could do this is through joule heated actuation, for actually trying to think about using things like liquid crystal elastomers, running a current through these, and actually driving electrically controlled motion. The big problem, of course, with any joule heating kind of actuation strategy is that this is not very efficient, and these kinds of mechanisms are very slow. We can also turn to electrostatics, things like DEAs or Hazel actuators. These are great because they are incredibly fast. I get very high actuation bandwidths, but I still need all of that rigid, bulky hardware to drive the large voltages required for their actuation. And so for us, we have been interested in what other materials opportunities do we have for approaching ways of electrically actuating these robots. For a number of reasons, architected materials should be inspiring kind of ideas within this space of soft robotics. And for us in particular, we have been interested in kind of ways of thinking about auxetics for actuation. The big problem, though, is in most of this space, there are kind of bespoke design and manufacturing methods for all of these types of architected materials. And it'd be great to find ways of kind of streamlining the design and fabrication of these complex architectures. So a colleague of mine, Jeff Lipton at MIT, had started working on a new class of auxetics called handed shearing auxetics. And unlike conventional auxetics, which kind of have this symmetric auxetic angle, handed shearing auxetics do have this chirality to them, which allows us to think about ways of interestingly coupling rotational movement with extensional motion. And what that allows us to do is actually conceive of ways of driving shape change with servo motors. I actuate or rotate one end and drive displacement of the other. The big problem, or I'm jumping ahead a little bit, but one of the big opportunities that we see for this is if I'm just driving these types of bending actuators or complex actuators with servo motors, I get to replace this whole pneumatic setup with something very streamlined and simple. I get to return to electronic power, low form factor of servo motors. I can work with traditional components and not these gigantic kind of infrastructures that are otherwise needed. This is another actual type of system that you can design, not just a bending actuator like you saw there, but actually a kind of platform with multiple degrees of freedom. And so by just changing the rotation angle of my servo, I can get very complex shape changes that would be kind of difficult to achieve with pneumatic systems or even some of these other types of actuators. And so you can see this extending, compressing, bending, twisting, very complex actuation, again, all through servo motors. The big problem with auxetics is, again, they're kind of limited to how you achieve that architecture. And for the HSAs, we use Teflon because of its high strain at failure. And we had to actually make these HSAs through rotational laser cutting, which is not a great reproducible process. It gave rise to a lot of kind of reproducibility errors. And we really were trying to think about ways of moving beyond this very limiting kind of manufacturing approach. So in my last year at MIT, I was able to bring in a carbon M1 printer, where we started using the proprietary resins from DLP and carbon to actually create these types of architected motorized structures. So very quickly, again, it's this elongation at break that allows us to have these living hinges within these auxetic materials. Teflon has elongation at break that is incredibly high, 300 to 500%. And we had a couple of different polyurethane-based resins that we were interested in using from carbon. Specifically, we were pretty excited about their FPU or EPU resins, which stand for flexible and elastomeric polyurethane. Without going into too much on the characterization, what we were able to see is that qualitatively, we saw identical performance, which was really exciting to see. So instead of laser cutting these, we can now print them from a couple of different materials, not just Teflon. And again, qualitatively, we do see some nice similarities in their behavior. The EPU is very soft though, and so you can see these kind of weird buckling behaviors at large deformations. You can do some really interesting things too. We're not limited to one tube and laser cutting. We can create concentric assemblies. We can think about combining rigid endoskeletons surrounded by flexible exoskeletons. And so we wanted to showcase what some of those opportunities might look like. So this is one of these kind of multi-degree of freedom platforms. All we did was simply nest concentric HSAs, and from that get a much higher block force without really compromising the servos in any way. And so looking at blocked force here, you can see that these kind of concentric HSA assemblies give a much higher force given servo rotations. And then we just wanted to compare from the kind of bending point of view how the performance of FPU would compare to something like Teflon. So we made these kind of bending fingers, created a setup on an instron where we grasp around an object and see what force is required to pull that object out. You see here Teflon fingers, our flexible polyurethane fingers, these very soft, very compliant kind of floppy elastomeric polyurethane fingers, and then these hybrid designs. And what we see from the grip force analysis is that Teflon and flexible polyurethane perform quite similarly, which is good to see. That APU really is too soft to generate much force at all. And very interestingly, even though that hybrid design isn't bending as much, that rigid endoskeleton does give us a way of thinking about having higher grasp force. And so for this particular design, we are seeing what we can do with greater torque servos and optimized designs. I also want to point out that this was done in the middle of the pandemic. So we were working with pretty beat up servos, and we would love to go back and kind of redo some of the servos and actually get good servos in that, not have the project disrupted by everything with COVID. So in short, we're able to 3D print these new types of architected materials. We've really kind of expanded the material space here, and we are very interested in building off this work, not only in designing the HSAs in new ways, but seeing these kind of HSAs in new different types of soft robots. I really want to get to the discussion because I know that's a big part of this, and I just kind of wanted to end with this slide, showing a little bit about my vision for where we want to go. By closing the performance gap, literally of built and biological, we see soft materials having a role of helping us create new types of robots that generally can help in environmental and in ecological stewardship type applications. I'm very interested in thinking about domestic and assistive robots, as well as what we can learn here on advancing kind of the medical robotics space as well. This work is done with a number of people which are very dear to me. And so I'm not going to say all of their names, but I'll give specific shout outs to my PhD and postdoc advisors, Jennifer Lewis and Daniela Roos, respectively. I am very grateful for a number of organizations that have sponsored this work, namely the Wyss Institute and the Schmidt Science Fellows, which supported my postdoc. I'm now at a point in my career where I have this incredible privilege of leading my own team, and I just wanted to showcase the people that I have the opportunity to come and work with every single day. I truly love these students. They don't even know how much they mean to me right now, but our lab is growing a lot. And if you want to learn more, I've put the link down here. Admittedly, we're still behind on updating the news, but nonetheless, we do try to keep the research vision and the publications updated as much as possible. With that, I know it was a whirlwind. I wanted to share a little bit about this vision going forward and how we've explored what robotic materials might mean in the context of these soft sensorized and architected materials. And so with that, I'm more than happy to take any questions, and I look forward to the remainder discussion. Thank you all.
Thank you. Thank you so much for your great talk.
Thanks.
So now let's see, we're going to have the question and answer, right? So Binbin and I will co-host a question and answer session. Yeah, so I think the rule is like if you have any question, you will raise your hand, right? Otherwise, you can put your questions in the question and answer or the chat. So we'll read it from the audience. So let's see. Yeah, let me ask one first question just to start. Is okay?
Sure.
I mean, I think it's very exciting. I mean, you showed all these works about integrating sensors into actuators. So that is a very exciting topic. I'm also agree with, and also a lot of people are also doing in this direction, right? So you're definitely show some integration of the sensors into mobile robotic manipulators, right? With all these multimodal sensing ability. So my question regarding this is, how do you see when you are trying to integrate sensors into actuators, right? When you scale up or scale down, what are the challenges you can see like in the future, right? If you want to make it really small or you want to really big, right? Potentially have all these weight, all these effectors. How do you see the challenges?
Oh man,
yeah,
in this manufacturing,
very interesting topic. Yeah,
absolutely. I always wrap everything back to a manufacturing limitation, because manufacturing at the end of the day limits what our opportunities are. There is not a good manufacturing method out there that would allow us to span every single scale possible for any material possible. Manufacturing methods are very much limited to their compatibility with certain materials and very limited to certain length scales. We are working on something right now that might be somewhat scale invariant. And unfortunately, I thought I would have it ready for this talk, and we're still trying to get the final touches on this system. The short answer is that I think you have to rethink what sensing is. Mm-hmm. I think you have to rethink how you're achieving perception. And that's what the last part of my postdoc was really focused on, was what happens when you're actually not using an ionogel or a liquid metal or a conductor to actually sense. I think that therein lies the opportunity of thinking about how can you still hold on to that sensing without necessarily needing to pattern a conductive material. But this is a huge question, and I don't have a very good answer for you. It's going to be manufacturing specific to how we bring these actuation and sensing capabilities together.
Yeah, I definitely agree. And from my point of view, I also think like the application wise, right? Totally depends on application. What our challenges are potentially also lie into the material properties. And also, as you mentioned, manufacturer, for example, we are mostly interested in medical robotics. Then the material wise, you have to have biocompatibility and all these requirements, right? All these raises challenges. But I do think, yeah, it's a very interesting topic. Yeah.
I will kind of follow up too, and I completely agree with you. I do want to add that it depends on what type of sensor you want to, and yes, what sort of resolution you need. And to the credit of many people working in this space, like I do think those individuals thinking about how vision provides sensing are actually kind of onto something, because if I have a camera and I'm able to use that camera to perceive, I am able to bypass many of the manufacturing challenges that would come with trying to create very dense arrays of sensors for for sensing. Yeah. So that's another kind of way of explaining what I mean by rethinking sensing entirely beyond just a conductive fluid or some conductor. Really thinking outside the box.
Yeah, thanks. I think the next one will be Yu Shuo.
Yes, can you hear me?
Hey, how's it going?
Good. Yeah, so yeah, Ryan, thank you so much. It's great to see you talk, and it's a very inspiring, and yeah, it's awesome talk. I also work in soft robotics. Yeah, we actually kind of a neighbor. I mean, also in C-Cell.
Yeah, I know.
yeah. So, but very great talk. So I have two questions, and I would like to seek your suggestions or comments. The first one is like this: for your second project, you assume the robot deformation is kind of PCC, kind of continuous or like a constant curvature.
Yeah.
So for some other robot, the soft robots may not necessarily exactly the constant curvature. So in your point of view, do you think is there any like a good or general or ubiquitous representation for soft robots? What could be a good representation if it's not continuous or constant curvature? The second question I would like seek your suggestion is like this. Some people ask, soft robots, they have this mechanical compliance, so they will adapt to different shape. They may not require good sensing capability to rely on this mechanical mechanical compliance. And like traditional maybe rigid robots, they can rely on the sensor to respond, so they can maybe not destroy or damage the objects. But soft robots have this mechanical compliance. Why do we need a very precise sensing? Yeah, it'd be great to hear your comments about that. These two questions. Thank you.
Yeah, no, thanks. I'm going to start with the second question because I think that goes back to what I was trying to say about this focus on physical intelligence. There is certainly a role for how we think about sensorless behavior. There is certainly a role for thinking about how mechanical properties of materials play into some performance that we don't have to compute for, that we don't have to have sensing for. But you still need sensors. You still need some sort of brain controlling that system. We're putting ourselves in very narrow bins when we say, I can feel for something and grasp it without any sensing. And that's true. You can like design soft grippers that do these things and I don't have to program. But the second I want to begin thinking about more complex systems, I have to recognize there has to be some computational intelligence still. One of the things that's really fun about these two projects I presented on with like autonomous grasping and the kind of machine learning for perception is that the grasping project is a very, very, very simple sensing. We're literally looking at resistance changes from 6 contact sensors and getting those types of emergent behaviors just from compliance of that system. We're not controlling for how it postures down. We're literally just looking for thresholds of resistance change, and we get these really cool things. That kind of rides that side of really not needing a whole lot of sensing. You still need maybe some, but you don't need a whole lot. It's when we start moving to more sophisticated performances that I have to disagree with people in the field who say we don't need sensing. You would not function well without sensing. Most organisms wouldn't function well without sensing. Bridging that physical and computational sides of intelligence is what we have to do next. We have to ask these hard questions of how much sensing is appropriate for certain applications and how much isn't. And we have to ride that balance, I think, a little bit more strategically than we have been. It's a very hard question. It's going to be a debate in this field for as long as the field exists. But I think it's a really exciting one. And I particularly will be pushing forward on how to work towards better sensing because I think it's needed.
Yeah, thank you.
Yeah, to your second or your first question rather on the general description, this is a very fair point. I do not want to argue that PCC is going to solve all problems because it's a very specific subset of continuous robots. One reason that we were so interested in PCC descriptions is that if I think about these soft robotic forms, elephant trunks, octopus tentacles, these kind of very continuous biological forms, many of them would fit that bill for being appropriately described by PCC models. I don't have a good question or answer for you on how do I generally think about these things too. And one of the big problems with any machine learning based approach for perception is that I will still have to come up with some basic description of kinematics that I can learn too. I think that in many ways, soft robotics needs to advance how we think about automated design and computation so that those insights can inform how we actually design these systems. In other words, Daniela Roos and Wojciech Matusek and many other people at MIT that I had the privilege of working with, they are working on those really important insights right now. And what they learn, I think, will ultimately tell us how to bridge that sim to real gap of meaningfully using machine learning to control these types of systems.
Thank you. Thank you very much.
Thank you.
I think it's a great discussion. I basically also, I just want to add a small comment here. I think basically it's more about the trade-off between the computational intelligence and the physical intelligence, right?
Yeah.
I mean, it's a hot topic, and normally people call it morphology computation if you use pure soft robot adaptation, right? But of course, I think you can take whatever you use and try to make your system have the best performance. That's the ultimate goal, right? So, and how to bridge the computational intelligence and morphology intelligence. Maybe that's the ongoing hot topic, and you need to make a lot of trade-off. Yeah. So that's
it's such a cool question because at the end of the day, right, it teaches us a lot about ourselves. And it's like, what are these trade-offs? And I think we won't actually be able to ask that question until we can create a machine that we can almost have a knob on of how much is computational intelligence and how much is physical. And until you can create that artifact, you're not going to be able to answer that question. And so that's one reason why we are so focused on how do I actually create materials that will bring about these distributed sensory motor capabilities? Because if I can turn the computational side off and run the same experiment, then I get to that point of asking these really cool questions of how much do I need versus the physical side versus the computational.
Yeah, exactly. I think eventually maybe we'll build like a exactly similar to a soft animal type of robot, right?
Yeah.
So these are computation intelligence and morphology intelligence. Okay, all right. So let's see. Our next question is from Abdon.
Hi, thank you. Thank you, Ryan. It was a beautiful, beautiful talk. I really,
thanks, Abdon. Really appreciate it.
I really like that you show like these 3 different kind of branching out projects, but they're all complementary to each other, right? And I wanted to ask you about this, right? Because sometimes as scientists, we fall into the trap of the novelty, right? Yeah. Or the we do things for the sake that they're new, right? But I think it's very interesting that you show how servos have been around, they're quite established. You can buy them from Amazon, right? And you can bypass some of the limitations on some of the other like much more fancy or modern designs and materials, right? And I think this poses brings a lot of opportunities, but also challenges on translating these designs to industry. That it's not sometimes a bit resistant to these changes, right? So I wanted to ask you, what's your perspective, or where do you see these opportunities for bridging these new materials, new designs with some of the other not so fancy but more reliable and established technology like servos?
Yeah, I want to begin by saying that Jeff Lipton, who's now at the University of Washington, was a co-postdoc with me at Danielle's lab, and he really kind of inspired this thinking in me of saying you don't have to like go all in on new materials. Like you have to look back and say, what are we leaving behind that could be brought along on the journey? And I do have to credit him a lot with him kind of flicking that switch, making that neural connection in my own mind of thinking about, oh yeah, that actually makes a lot of sense. I do think when I talk about this idea of robotic materials, that we're not just talking about creating materials that are soft. I think there's a whole role of designing material systems that work around these rigid hardware components. So you don't just have to work on new actuators or artificial muscles. You could work on new architected materials that are specifically designed in a robotic context to work with servos and electromagnetic systems or electromechanical systems. At the end of the day, nature does really well. I still hold that like synthetic systems can outpace nature. Materials has a role to play in both of those opportunities. How much do we make it like nature, and how much can we use materials to outpace nature? Because the cool thing about robotics, I think, is that we're going to learn, again, a lot about ourselves. We're going to learn a lot about how biology has figured this out, but we need to figure out how to outpace or how to go beyond, because at the end of the day, if we can do that, we would tap into some really cool opportunities of using robots to really help us tackle some of these huge challenges. And so my group is right now at a split. You can group the subgroups on who's designing new materials and who's designing materials for servos and controllers and thinking about those types of strategies. And I do feel incredibly privileged to be at Northwestern because the colleagues who sit on either side of that are leaders in their field and are going to help us kind of lift up that vision. And so in full disclosure, we are working on both sides of that, and we see robotic materials riding that interface, hopefully in a good way.
Awesome, thanks. Looking forward to see all that cool stuff coming out of your lab.
Hopefully soon. We've got some cool stuff, and I can't show it, but we've got some really cool stuff coming.
Great. So the next one is Jingtian.
So I think my question is pretty similar to the previous one. You have answered about the computational intelligence and physical versus physical intelligence. So it's pretty much answered. I would like to ask you about your vision on this. So we already see Starship robots running around to deliver food, and they are the good examples of like robots based on hard materials and conventional electronics. So when it comes to the soft robotics, would you so one approach, of course, is to develop the electronics so that they can use the same electronic machine learning systems. But other people also want to explore like the chemical-based or like physical-based systems, but currently the stage is much less developed. But when you look at us, we are physical computations. So do you expect a more rapid development of this field, or do you think that this will be more advantageous in the soft robotics in the future?
Yeah, that's a great question. Speaking of food delivery robots, this is kind of where on slide 2, I was talking about we have to contrive environments, or we have to construct environments for robots to thrive in. If I took that food delivery robot and said, go down the alley and then go down the forest trail and give it to my cabin in the woods, it's probably not. It's going to be great so long as it's on like a sunny day going on a sidewalk with pedestrians it knows coming in the right direction. I'm creating the scenario for you, right?
Right.
And so for us, it really is about like, let's appreciate what robotics can do, but recognize that as soon as I put it on a real world environment, when I perturb that contrived environment just a little bit, it falls apart. We're going to find that out with autonomous driving, for example, where we can contrive the environment with a roadway, which we can regulate and write policy for. But as soon as I want you to do something else, it's going to become difficult. I think that if I want to get away from an electronically kind of integrated approach, if I want to rethink how to do all these capabilities, say by chemical means, that's kind of what we were trying with Octobot. So chemical fuels are interesting because their energy density is huge compared to even batteries. There's been really exciting works of trying to figure out how to use chemical fuels in these contexts. There's some really cool work in even microrobotics where I can use a chemical fuel as a very dense energy supply to actuate, say, shape memory alloys. But it's still so hard in my mind of thinking about how to integrate that with some robust perception or control strategy. And that's where we were running into problems with Octobot. We can use that chemical fuel for actuation, but that substrate of the liquid and the gas, it doesn't bode well for how to actually think about sensing or how to actually think about control. It's really tough to kind of think about, in my mind, how I would work on that vision of rooting every design aspect around the use of a fuel. Nature has figured out how to use chemical fuels, but works on ways of integrating, say, like action potentials and ionic conductivity and sense. Like there is some connection to that. And I think that if you want to work on that space, you do still have to recognize that nature doesn't purely chemically fuel everything. It does translate kind of all this over into ionic conductivity and these other things that we could also do with conventional electronics. I'm giving you a very fuzzy and horrible rambling answer, but I really hope.
I really like it. It's like, I mean, I'm not in the robotics field, so I think it's a very good vision.
I mean, this idea of this like tetrahedron showing all of these things like together is kind of the point there, right? Like I can bring a chemical fuel to the table, but it only satisfies parts of those needs. It's not going to satisfy the entire kind of robotic functionalities that I require. And that's kind of the short answer to your question is chemical fuels are interesting, but I don't know how to bridge them to fold in the computational or control needs.
Yeah, I think, yeah, that's a great point. I feel like also the similar for soft robotics, if you want to realize complex behaviors, normally you need programmability. That's normally we call in material. So if you cannot control their behavior precisely, or I mean complex shape, right, or behaviors, it's very difficult. And also regarding that, there are also some speed issues, right? If it is too slow, then you cannot really use it for real world applications. I think there is a trend converging to some, for example, electrical actuation and also magnetic actuation for untethered robot. I think there is a trend there, right? So because of the application driven in certain area, right? Yeah, I think this is a great discussion. Let's see, our next question is from Jin Yang.
Oh, hi, Ryan. This is excellent. I'm postdoc at the Wisconsin Medicine. Yes.
Oh, awesome.
So, yeah, my question is so I'm wondering if I want to have some robotics that can be quite small, like about a micrometer, or like I want to have some robotics that can be a much larger length scale, like in the order of the meter. So do you have some comments about the 3D printing or manufacturing, and also controlling or like application for this robotics at different length scales?
Yeah, this is kind of maybe following up a little bit on one of the earlier questions too about how do we think about this on any time or any length scale rather. Yeah, we are thinking here at Northwestern of how to go small. Like we are trying to think about ways of additively manufacturing a cell scale robot, and that's tough.
Oh.
It's really tough. When you hit a certain length scale, you free yourself from thinking about certain constraints. So in everything that I think about in soft robot design, my goal is to get it untethered. I'm not necessarily thinking about anything smaller than, say, a beetle. I would like to think on like the beetle to human link scale, because that's kind of where we see opportunities for robots going about solving real world challenges. But if I go below a beetle, like I can think about using electric or external fields. If I'm working at a micron link scale, well, a square millimeter is like a gigantic playground. I don't need to make that thing entirely tethered. I can use fields to kind of perturb it and move it around. And so I alleviate some of the needs that I might have in terms of actuation or even control. I think some of the really cool stuff happening in this space of thinking about small scale is really coming out of Professor Xiaoguang's group at Cornell University, where they're looking at kind of traditional electronics manufacturing methods of integrating kind of this physical and computational intelligence within microfabricated systems. Don't quote me on this. I think they're on the order of like 20 to 100 microns on link scale, but they are basically kind of like Jeff inspired me to not forgo the servo motor. They are very much saying, let's not forgo all of the work that we put into microfabricating electronic systems, and let's use those tools to explore these challenges as well. I think that's one opportunity to look at, is to think about how to use those manufacturing methods, as Professor Cohen and his group are doing, to look at that scale. Otherwise, it's a whole open question. I mean, we have like a number of conversations on this at Northwestern. And, you know, I can tell you from our thinking, we're not able to think about link scales below 100 microns. And that's including probably about 4 different materials. It's a really tough problem, but it's a really cool opportunity too. Yeah, that's kind of all I have to say on it, because it's super tough. But at that link scale, I would like encourage people to recognize that, yeah, you are free from, you know, some of the constraints of building at that beetle to human body link scale. You can kind of reinvent what actuation is.
I see. Thank you, Ryan.
Yeah, thanks.
Yeah, this is a great discussion, I think, about the scaling, right? Scaling down is always difficult.
So
I'm doing, like in my lab and also my previous lab, we are doing mostly small scale robotics devices, right? So normally you need a very fancy manufacturing methods like MEMS techniques and all flexible electronics, all these small scale fabrication techniques to really create the sensors and actuators, and itself is already very difficult. But the impact could be high. I can see, like in Northwestern, right, you have John Rogers and many other colleagues there doing great research in scaling down all these sensors, actuators. I can see eventually it should be very beneficial for the medical robotics.
Oh, absolutely.
Yeah. Although it's very challenging, I agree. Yeah. So next one, I think, is from Jen. Yeah.
I think Xiaoguang comes first.
Oh, okay.
Yeah.
I missed that. Yeah.
It's okay. Hello, everyone. So my name is Xiaoguang. Yeah. So I'm right now assistant professor in Duke, and I was a postdoc in John Rogers' group. So,
awesome. At Northwestern?
Yeah, at Northwestern. Yeah.
Awesome.
So I know many of many of you, like I know in the panelists. So I basically have like a few questions about the your sensors and actuators, and just give you some background. Like, since I was like doing flexible electronics and metamaterials, and somehow it converges for me to try to also do programmable materials, right? Yeah. So that's a very natural kind of like a bridge. And so, so for software robotics, I'm thinking of like the degrees of freedom, like the infinite degrees of freedom is always a problem, right? So how many like actuators and the sensors right now, like how maximum number of actuators and sensors you are actually using right now, like in your systems? And do you see a problem, for example, in the sensor distribution and the actuator, the number of the actuators you need to actually deal with this under-actuated problems, right?
Yeah, I mean, it's a great question. I don't know if I can even answer like what we need or what we're after right now. I would say like on the materials side of the group, focusing on new materials for these types of systems. We are just simply motivated by the fact that one thing we don't do well in soft robotics is even explore this idea of distributed sensory motor capabilities. In other words, like I showed you an arm with 12 actuators and I showed you a finger with 2 modes of deformation. But if I think about like my body, I'm able to selectively neurologically address all these different muscles and get this whole range of motion. And so what we are actually working on right now is trying to think about what materials would enable that exact sort of addressability, actually creating these types of structures. I'll let you know based on how big we can make them or how small we can make them, what sort of number that we need. We are on that space though, very much looking at how does nature do this? And we are not thinking about it in, I would say like a soft robotics way, where it's just, let's put a bunch on there and see what motions we can get. We're not doing that, except for that kind of auxetic side where we're just seeing what assemblies of motors and HSAs give us. On the material side, we are really just looking at what does kind of this idea of distributed sensing and motor capabilities mean for how we design these materials. And it is a scale problem, it is a manufacturing problem, it's a performance problem, it's all these things. We have some really awesome funding coming in from Navy to actually do this, which is really cool because this is one of the projects that I've been wanting to work on for a very long time. On the sensing side, that comes down to what you're trying to sense, right? Like you all in John Rogers' group have done wonderful work, like trying to think about dense arrays. That's going to be important for tactile sensing. How much tactile sensing you need is going to be dependent on your environment and your application. For us right now, I can probably safely say that we are more focused on the proprioceptive side, because in the context of control, as we see it and as we've been trying to tackle that problem, that is more important than the tactile side for now. Of course, as soon as I take a continuum robot, if I even took that arm that I showed and had it actuating against something, the neural network would totally fail because we haven't trained it to be in contact, and contact is very difficult to account for. We still think though that there's some really cool opportunities for using proprioceptive in a kind of multimodal way to give us not only proprioception, but maybe also tell us something about contact sensing. And Cosimo and I have done some other work where we use disturbance observers to basically use motion capture to predict not only shape, but also the direction and amplitude of contact.
I see.
Not with specialized tactile sensors, just with the cameras that we have.
Okay, well, thank you. Yeah. And can I actually ask another question? I wrote it in my panel, but it just disappeared. So how do you foresee the intrinsic limitations in your soft materials sensor and also actuator? Because like, for example, in terms of response time in certain limits, and especially if you are considering physical intelligence, right? Then speed becomes very important in that sense, yeah. That's
what that grant is working on. How do we go faster?
Okay.
How do I answer this? It's a super interesting problem. And I think that when we look at soft robotic actuation, if you're not focusing on improving the performance of practical actuators, you're not going to see kind of your embodiments make a huge impact in 10, 20 years. You do have to tackle these challenges head on. And unfortunately, actuation, in my opinion, is probably the hardest challenge that we could take on. I have some level of hope and a lot of humility looking at nature and recognizing that nature figured this out. Muscles are not super high performance compared to like a DEA, but the way in which you can address them, the way they self-heal, the way we know all the advantages of muscle, like, in my opinion, that should inspire every single person working in soft material science, because that is just this phenomenal example of exquisite control over architecture, translating to this incredible thing that nature has figured out how to design. And so in our group, this is at kind of the forefront of what we think about. in all honesty, it's one reason why we're not giving up on servos, which are fast, which can help us towards that goal of fast actuation. It is a more streamlined way than thinking of purely thermomechanical approaches.
I see. Okay, thank you.
Yeah. How's everything going at Duke?
Oh, it's great. Like COVID is like gradually like not influencing your life. So like the lab is right now the colleagues comes back to campus and you can get a chance to talk to everyone on the corner of the hallway. That's really nice. Yeah.
Duke is a great university in the southern part.
Yes. And weather is really nice today.
Anyway, it's a great introduction discussion about the like sensing integration with actuators, right? About the degree freedom. I think it's a great discussion. I think probably I mean in the future, if you want to sense any actuator, you have to consider both actuator and sensing components the same simultaneously, right? Because normally depending on the application, so the state you want to sense will totally, constraint the sensor design, right? So it's a like a joint problem, right? So I think that's great. So our next question will be from Jin now.
Thank you, Xiaoguang, and thank you, Ryan, for the nice talk. I actually have two questions, and the first one is I heard you mention in your questions like you want to go smaller and go in tensor. I mean, but for go in tensor, if the in-tensor actuation, it also indicates that you need in-tensor sensing. Then do you have anything in mind how to do in-tensor sensing? Because I imagine that will be very difficult. And the another question is that people always say like soft robots, they have advantages as in they have better human and human machine interactions, and they have a lot of degree of freedom, so they can go to very complex environments. But like many biological systems, especially for the more advanced ones, like human beings and all of the animals, they are more like a hard skeleton coated by soft actuators and soft sensors. So what are you thinking that would be even the future for the soft robotics, or maybe the soft robotics can stay in its way like purely soft, but they have more advantage than the kind of like a hard soft systems? Yeah, that's my question.
Yeah, those are great questions. I mean, on the sensing side, going small, that's tough. I mean, I think Professor Seedy's done some really interesting thinking on what perception is and draws like really great analogies, for example, with like single cells. Single cells are not sensing in super sophisticated ways like multicellular organisms are. They're relying on fundamentally different insights. They're relying on chemical gradients, changes of surface potential or membrane potential, rather. Their sensing is very rudimentary. And so you have to compromise what like that degree of sophistication is, which is hard to define as I go smaller and smaller. But I do want to still point out Professor Itai Cohen is doing really cool work where sensing isn't changing much. Like computation isn't changing much. He's just figuring out how to put it in a smaller and smaller package. And I think that's why he's a clear signal for the field to pay attention to, is he's showing us ways of kind of bridging that computational and physical intelligence at new length scales. So that's kind of my answer roughly to your first question. For the second question, you know, we were working on with Octobot an entirely soft machine, and it was more just kind of an adventure of, can you do this without hardware? Yes, it's entirely soft. Yes, we were kind of like really trying to celebrate the opportunities one would have by not having a totally rigid system. At the end of the day, you do have to strike a balance between rigid and soft. And that's one reason why we are interested in kind of creating these types of architected materials where if I'm working on that servo, which is very rigid, I might be able to architect something around it, which strikes that balance of compliance while kind of shielding away the rigid component. There's really, really, really exciting work coming out in the architected space of thinking about how architecture can tailor compliance and even shield the presence of rigidity that I think that this community has to listen to, because it just goes beyond a simple modulus, and through structure and design and all these other things allows us to actually imagine a robotic materials approach for thinking about these types of balances between soft and rigid. But yeah, it's an interesting question. And again, I think it's going to be difficult to ask these unless you can get better actuators and you can get more bio-inspired systems to really understand. Like if we have a knob for pure computational intelligence and pure physical, like pure hard and pure soft, like we need to be able to have that ability to dial too.
Okay, cool.
Yeah, thanks for the good question.
Yeah, thank you.
Thanks.
Yeah, I think regarding this, mostly, I think in your last part, right, your work is mostly about architecture material. From my point of view, it's more like the architecture of like a mechanism or transmission. It looks like you are using an actuator with 1 degree freedom and just transmit to the end, right? So yeah, adding on this Jen's question, I'm just curious, for this kind of material, how could you secure the compliance? I mean, originally you have in other soft material, right? Because the material you are using are relatively rigid. How could you make it safe? Yeah.
Yeah, I mean, through architecture, we can play with that a little bit, right? On its own, we can think about more porous materials. We can think about kind of flexibility, like, I actually have one here. I forgot I had these. So this is like one of the HSAs. And so it is compliant by all means. It's rigid, but it is still compliant. And it's that careful balance of architecture that allows me to have that. In all honesty, like it's difficult making these architected materials. And that's kind of one thing I had to breeze through because I was running short on time, is that a lot of those are difficult to make. You have very specific kind of bespoke manufacturing methods. We do have to come up with ways of creating kind of more multi-material architected materials to get that balance too. And so kind of a percolating theme in our group is to take some of our printing methods and think about multi-material architectures that would allow us to do this in maybe a sense that you're thinking of, which is more add that modulus knob alongside the architecture knob.
Yes. All right, so the next question I think is from Binbin.
Hi, Ryan. Fantastic talk.
Thank you.
Really, truly inspirational.
Thank you.
Yeah, I'm quite curious and interesting about the last slides of your presentation. You mentioned like you will be working on medical robots, right? That's the very hot topic I'm interested in. Yeah. So I'd like to know more about your vision and your future plan for your group in this direction, because as I know, like medical robot is always quite challenged. Like you should consider about like powering, signal transmission, communication, biocompatibility, biotoxicity, and even like protocol application. That's quite challenging. So can you comment on this direction that you want to working on?
Yeah, I can give you some hints as to where our thoughts are. The short answer lies in the fact that soft materials are not as high performing as some of these other robots, right? And so when we think about Da Vinci robots, or we think about other systems where we're thinking in surgical means, like, yeah, you can make some soft systems that might help there. You might be able to think about some interesting devices for different procedures, different internal procedures, whatever. One of the things that I'm really trying to explore is we don't need like soft materials going to work for us. So I know there's like a lot of interest in kind of exoskeletons or rehab or these types of things. I actually don't think that these are the way to do it. You're just not going to get, in certain contexts or even the right like kind of operating conditions, good materials to help you do that just yet. That's going to require a lot more advances on the actuation side. We kind of see it more as robots to augment performance or extend performance, not restore it. So instead of an exoskeleton restoring motion when it's lost, we're thinking of what medical opportunities are there for us to extend what the body can do or technologies can do through some, say, wearable or implantable robot. That could be everything from sensing some analyte and responding in very simple context to it. That could be trying to do something like correcting motion where a large force isn't required. Those are the types of themes that we're looking on right now, of not trying to ask the soft materials to do more than they can probably do. We're trying to see what opportunities lie in extending capabilities by virtue of the fact that we have these soft materials still doing very interesting things. There's a lot of people here at Northwestern, there are at MIT too, but at Northwestern working on true robots for a variety of human interaction purposes. And so they're not medical in like a surgical sense or a therapy sense, they're more like kind of medical in a rehab or a telemedicine sense and all these types of other things too. And they are guiding a lot of our thinking in this space of how do these materials have a role to play in those interactions beyond just they're soft. Like, is there something a soft material can do to help inform those interactions? There's a big push for us to think about kind of the haptics space too, and how haptics has a role to play in telemedicine, to restoration of sensation, to all sorts of things. And that's hopefully kind of the themes that hopefully shares a little bit of the themes that we're kind of working on.
Great. You just mentioned the augmentation, because I recently watched a documentation video from Professor Hugh from MIT about the augmentation. So I think that's a good video source for everybody to watch, and it's truly inspirational.
Oh, absolutely. And I think the augmentation part is interesting, and it's tough, and it's ethically challenging, and there's all these things that we have to keep in mind. I also want to comment on, augmenting performance does create a whole new set of discussions that we have to have. And it is also hard to say, are we going to work on that when there are other ways in which we can solve much more immediate and pressing challenges? I also just think it's important to recognize what the true opportunities are for these materials. And I think you're going to see them really have a domain here. And I think it is worth still exploring, because there are a number of ways in which we can enhance life and well-being by augmenting current either bodily capabilities or the limitations of technology right now.
Yeah, great. So so before wrapping up today's talk, I'd like to give you a bonus, it's a bonus for being a speaker in our society. So do you want say something about the future recruiting plan for your group, like any specific students you want to recruit through our platform? Hope this is all one of the goal of our society, right?
I'd be happy to.
Yeah,
I mean, so we are actively recruiting at all times. I take a very people first, paper centric approach to my group. I very much am intentional in the ways in which we build community. I have benefited from that time and time again. And so now that I'm at the driver's seat, I very much try to follow in the footsteps of the incredible mentors I've had to create such an environment. One of the things that we do is we intentionally bring in people who are going to want to think differently. I mentioned previously, it's like covalent bonds and servo motors. There's a clear divide at the beginning of who knows what's what. And it's been really inspiring to watch my team help each other share or develop a common language. And so from my point of view, we are constantly looking for people who do want to work at this intersection of disciplines, who aren't satisfied with just anything other than trying to work towards the very hardest of challenges. I mean, actuation for us is that hard challenge, and we need materials people. We need people who are interested in manufacturing. We're interested in people in the group having robotics. And by the end of spring, we would basically have manufacturing, robotics, and materials people all in the group. So if you come with that mindset and you're excited by those ideas, we take a lot of time to make sure that we interview. I will say that I get about 15 emails a day now asking for prospective students. So I can't always address those emails, and it's just unfortunate that I can't, but that is the way things are. And we just do our best to bring in people who want to work in this kind of new way.
Great. Thank you. Xiaoguang?
Yeah, great. I think it's nearly we are a little over time, but thanks again for Professor Ryan Truby for this fantastic talk today. And thanks all you guys attending this talk and ask questions, and also thank the audience. And most importantly, I would like to thank the organizers, Jen and Binbin, and the whole society to give the opportunity for me to host this talk. Yeah, let's thank again Professor Ryan Truby. Yeah.
Well, I also want to say thank you to all of you too, and Xiaoguang, you were great. And
you connect, later in person.
Yeah, no, absolutely. Yeah, and thank you for hosting, and hopefully at some point I can return the favor.
Definitely, I will attend many conferences related with soft material robotics, so we can definitely meet each other. Yeah, in the near future.
Yeah, looking forward to it. Yeah, and I want to thank
also
Binbin
medical
and everybody.
robotics. If you are interested, we are organizing an ISMR, like a robotics. It's in Georgia Tech. So just
Okay.
a small advertisement. There is a workshop, so mostly open to pre-tenure faculty members. If you are interested, I can send you an email.
Yeah, I'd be happy to learn more.
Organizer. Yeah.
Cool. Awesome. Thanks.
Cool. Yeah.
Yeah, and thanks,
Right.
Binbin. Thank you, everyone.
Thank you, Ryan.
It was great to be with y'all.
Yeah.
Thank you, Ryan.
Thank you.
I will be writing a recap for the for this talk. I will send you the draft soon.
Yeah.
Okay, sounds good. Yeah, thanks for all the patience.
Yeah, we will edit the video before publish on the YouTube channel.
Okay.
And we will let you know. And please comment if you have any questions on the video.
Perfect. Sounds good. Thank you.
Yeah. Great.
All right. Well,
Thank
everybody
you.
have a good weekend.
All right.
You
Have a
too,
good weekend. See
Yeah.
you.
Have a good
Bye-bye.
weekend.
Be well.
See you.
Bye.
Bye.
Bye.